Hello, everyone. I'd like to make the introductions of this webinar organized by Mozambican Commission on Dams with the partnership of many other companies. And we are here to talk about this important subject around sustainable management of sediments on reservoirs. For this session, you will join us experts from the field, namely Lara Gehrmann and Mr. Elder Guta from Artelia. We will start this webinar with a general information and agenda, as we find here. Next, we will have welcome notes by Mr. Carlos Bonet, the President of Mozambican Commission on Dams. After that, general notes about Mozambican Commission on Dams and what is our goal. We have Mr. José Matola, manager at Cahora Bassa Dam, who will make introduction of the speakers, and we will have the sections, the section 1 and section 2. With our guest speakers. After that, we will have the Q&A session. It will be open discussion with the participants. You can start writing on the chat where you are now, and some questions after the presentations. And in the end, we will have to find the closing remarks, which we can say the resume of the meeting. We will start with Mr. Bonet. Mr. Bonet is connected. Mr. Carlos, are you connected? No, but I think there's some issues on the connection for this side. But anyway, we have connected Mr. Guta already, Lara, and I think we have the conditions to continue with our session. We will skip this introduction. Welcome notes from Mr. Bonet. Maybe we can have his notes on the end of the section 1 and section 2. Regarding the information on Mozambican Commission on Dams, Mozambican Commission on Dams is a Mozambican organization which engaged with the major players in the dam industry in Mozambique. And we have members, institutional members and individual members. And we invite all interested on join Mozambican Commission on Dams. We have been engaged with the International Commission on Large Dams, the IPOLD, in many activities, which one of them are related to the events, the annual meetings. We participate also in the General Assembly meetings. Last year was in Gothenburg, Sweden, and we were represented by many of our members, including members from the Hidroeléctrica of Bassa and other institutions also. This is an invitation for all of us who want to join this committee. If you want to be engaged with the state-of-the-art on dam industry and hydropower developments, please just send me an email and you will make all arrangements necessary for this to join the commission. With no further delays, I will introduce here Mr. José Matola, who will be the coordinator of the webinar. And Mr. José Matola is a civil engineer. He graduated in Eduardo Mondlane University. He have a Master of Science degree in Hydraulic and Environmental Engineer from EHE Delft. He obtained with the distinction. He have now 29 years of experience in the field of hydrology and water resource management, and presently is the manager of hydrology and dam safety division at Cahora Bassa Hydropower Company, with responsibilities on management and connected different structures, the reservoir operation, and also management of industrial aquatic environment. Mr. Matola is member of Mozambique Engineers Association and is also being engaged with several organizations and participate in several conferences such as the MozCOLD, Hydro, Congresso Luso Moçambicano de Engenharia, Silujba, and he presented various papers on this conference. Please, Mr. Matola, the floor is yours.
Good afternoon, everybody. My name is José Matola, as Mr. Baptista said. Without delaying, I will be doing my first job here, which is to introduce to you the speaker of today. Remember that the issue here is sediment management on reservoir, which is an issue of very importance for all the people who lead with dams. Today we'll have two speakers, namely Lara. She's a project leader at the Hülskens Sediment, GmbH, a company that is specialized in sustainable sediment management. She has a master's and a bachelor degree in civil engineering from RWTH Hülskens University, with focus on hydraulics engineering and project management. She is also active member of the technical committee of German Association for Water and Wastewater and the MozCOLD, where she contributed to advancement of field on reservoir sedimentation. Since 2021, she participated and contributes to various national and international conferences, such as MozCOLD, hydropower and dams, and Sediment, and the others. And she's author and speaker focusing on sustainable sediment management solution for reservoir. Here is a very short CV of Lara. I know that she has more competence than that, but here is just a short CV. And then the other speaker will be Mr. Elder Guta. Elder Guta has a degree in civil engineering from Mozambique and a master's degrees in hydraulics and a PhD in sediment transport hydraulics, both from the University of Grenoble, Alps in France. Mr. Elder has 10-year professional experience. His first experience in Mozambique enabled him to familiarize himself with hydrology and water source studies, urban hydraulics and the hydraulics of infrastructure design. Currently in France, he carries out study in the field of river hydraulics, such as hydrological analysis of flood flows and the hydrological model of rainfall runoff in one-dimensional and two-dimensional hydraulic model, study and the modeling of sediment transport, and the river engineering, which has to do with dam sedimentation and the mitigation measures, erosion, and sedimentation control and flood control. Mr. Guta has published more than 10 articles in the Mozambique and International Conference, as well as peer-reviewed scientific journals. He is an active member of several professional and scientific organizations in Mozambique and abroad. As said that, we can see that we have a very competent people to talk about this field of sustainable management of sediment, and we are expecting to hear and we learn a lot of things from these fellows, these experts. As I said that, I will invite Ms. Lara to make a presentation on this matter, which is continuous sedimentation transport for long-term reservoir management. Ms. Lara, the floor is yours. You can start.
Thank you very much. I share my screen and I hope you can see my presentation.
Yes, thank you.
All right. So thank you for this short introduction. And I'd like to talk the next few minutes about the continuous sediment transport, which is a sustainable solution for sedimentation issues in reservoirs. When I think about the water, and I always like to be there. I think it's a very nice environment. We are working there, we are dealing with. But just under the surface, there might be hidden a lot of sediments. So what we might not see in the first impact are huge layers of sediments which accumulated over years, over decades. And that's a problem we need to solve in that century. The World Bank once said the last century was made to build dams and hydropower, but the next one, so that one we are living right now in, is about solving the sedimentation problems. And just to give a quick overview about how the sedimentation is resulting in a decreased capacity, I show you some figures out of a study published 2022 by Pereira from the UN University, and we see an overview, a global overview from the status quo of 2022, and you can see marked in the colors the sedimentation rate, which is in average in that country we can see. So in 2022, we had around 4 problematic countries where they already had a sedimentation rate capacity loss of 25% of their reservoirs capacity. When we skip to 2030, it increases. We have many more countries suffering under real capacity loss in the reservoirs. And when we talk about 2050, I just spared out the circles, the marks, because many countries are suffering under or will suffer under capacity losses due to sedimentation from between 20 to 30, 40%. Let's talk about desedimentation measures. Let's talk about how can we solve the sedimentation of reservoirs in a sustainable manner. And just to give you a quick overview of what I'm talking about, if I'm talking about the upstream water, if I'm talking about the reservoir, I'm talking about the water area, the lake area in front of the dam. There, the water is almost stopped in flow, so the sediment can just settle down. And we see thick layers of sedimentation increasing over the years. When I'm talking about the downstream water, I'm talking about the part behind the dam. And because the dam or the lake, the reservoir, is acting like a sediment trap, we have a lack of sediment inside the downstream water, resulting in erosion of the bed and the banks. So when we built the dams in the last century, we changed the morphology of our rivers, and now we are dealing with the consequences. So why are dams and reservoirs acting like a sediment trap? Because the flow velocity of the water is decelerated and the sediment can settle down to the bottom. The water can leak through the outlets of the dam to the downstream water, but the sediment is trapped inside the reservoir. And because of the sediment deficit that is now existing in the downstream water, the river still wants to transport sediments. We are facing erosion effects. So there is an erosion of the bottom of the bed of the river and also from the sides, from the banks. This can also result in instabilities of structures. For example, if we have erosion right behind a bridge fundament, this can result in an instability because there's not enough support any longer from the bottom for the bridge fundament. We can also get problems in front of the dam because the sediment masses, the layers, are adding another force on the dam, which was maybe not calculated in design period. What's also missing in the downstream water is sediment, diluted sediment, which transport nutrition. Those are used for the aquatic life and also for floodplain forest in the outside. We can see it in the River Nile, for example, in Egypt. There are a lot of complaints from local farmers that because of the building of the dam, now the floods and also the sediment floods are no longer happening, which is resulting in a decreased nutrient supply for the fields. And if you look until the end of the river, we can see a land loss in river deltas. There are some examples. For example, in Europe, we have Rio Ebro in Spain. We have examples in Brazil. We have examples in China and many other river deltas where we can see that since we built the dams, there's not enough sediment, which is aggregating in the river delta. And due to the elevation of the sea level rise, we lose land. The World Bank once said that by 2050, about 25% of all impounded waters will no longer be usable due to sedimentation. So that means even if we build more reservoirs, more capacity, with an annual loss of capacity from around 1 to 2%, we lose more sediment, we lose more reservoir capacity than it's built new. So this results in a real loss of capacity, even that we build more reservoirs. Here again, the site from the World Bank, the last century was used to build reservoirs. This one will be used to solve the sediment problems. But I don't want to talk longer about problems. I want to talk about solutions, about new attempts. So we focus at Hülskens, and I focus with my interest in the sediment transfer. What does it mean? It is, for example, explained in the ICOL bulletin about sediment bypassing and sediment transport. And we have different options, but all are focusing on the same. We want to transport the sediments from the upstream to the downstream to restore the sediment balance inside the river. So how does it work? We use floating platforms with an installated pump, and we use the sediments at the bottom of the lake, the bottom of the reservoir. We suck them in and transport them inside a transfer line until the drop zone. What might be a drop zone? We have different possibilities over here. First, we can put the sediments right in front of the outlets, so that by the erosive flow, the sediment is transported through the dam inside the downstream water. But we can also bypass it. So we put a bypass tube to the downstream river, and by that directly insert the sediments in the downstream flow. But we want to focus on sustainability, and we want to focus on a natural concentration of sediments in the downstream. So how do we do it? We measure the sediment concentration, and we calculated and designed the whole process that we just add small concentrations, low concentrations to the downstream, that the river can transport the sediments further. Because what we don't want to do is we don't want to add the sediment in the downstream river to have sedimentation right behind the dam. That's not the goal. The goal is to restore the sediment continuity, the sediment balance in the system. So how do we do it? We measure what we produce, we measure what we transport, the discharge, the mass flow, the volume flow, the sediment concentrations, and then we calculate by the flow of the downstream river how much sediment we can include. Here you can see what we also have in our design plan, in our design phase, what we consider. So we have on one hand the sediment inflow, which is coming inside the reservoir. We know how much sediment is already aggregated inside the basin. Then we measure what we transport in real time, and we can also measure the concentrations in the downstream river. So we have many different parameters we can put in our steering, because our system is designed fully automatic. That means it can work around the clock without operators, without people close to it. It's a remote controlled system where the operator just has a surveying position. So how do we do it? By measuring all those parameters, by knowing how much sediment we can transport, we need to transport, and how much sediment the river can transport. We developed a steering, we developed a computer program for the Sedimover to work, and then it's cloud-based steered. So it can work around the clock, and that is the reason why we can transport huge masses of sediment just in a low concentration, so that the downstream river can always transport the sediments further away. In that steering, in the full automation, we include the real-time measurements, we include hazards, we include weather information, river information, to have an overview on the parameters on site. And of course, if the Sedimover is facing a problem, clogging of the transport line, maybe an error in the system, maybe also a cut of energy supply, we are notified. And of course, there are people we have a service which is then going to the site and is doing maintenance on the Sedimover. But in the normal case, it can work 1 week, 2 week, 4 weeks, and on a regular basis, we have a maintenance program to check on the devices. What's also good that we have a cloud computing behind it, and we are very concerned about the transparency. So we have the possibility to give the operator the authority is also download the data, because what I in the figures is that, and the better you can do decisions based on the analysis. So it's really important to us to offer this data to see what is transported, how much will be transported, and how the river is doing with the sediments. I also mentioned the ICOL bulletin we contributed to, and in my introduction, it was always mentioned that I'm a member of the DBH, which is a national committee here in Germany, and where we contribute with our knowledge about the sediment transfer to guidelines which can be applied. And I'm very proud of it to tell that the last guideline, the DVHM 513 number 3, is about to be published soon. We got that in a preliminary version published in December, and now with the annotations made, it will be published, I think, in the upcoming month as a final version. I hope I could give you a small overview about how the system is working. Because of the full automation of the system, we are aware that we cannot block the full reservoir all in once, because maybe it's used in a different manner. Maybe we have some leisure there, some ship traffic, or maybe it is used for swimming, for recreational purposes. So we work in sections to move the sediment mover from side to side to, at the end, hand worked in the whole reservoir to have transported all sediments from the whole area in the reservoir. We can connect it to many different things. Maybe we can use trees. Maybe we can use earth anchors or bowls, because it's a very light device. It's floating, so we just have to handle forces up to 200, 300 kilograms. So it's very modular, it's very variable, the options we can choose over there. And because we know that not every reservoir is the same, better said, every reservoir is unique. We know that we have from small distances up to huge distances to transport the sediments. And of course, the pump we have installed on board is limited in the pump capacity. But that does not mean that we are limited in the scalable distance, in the distances we can transport the sediment, because we work with booster pumps to prolong the transfer line at that, to be able to work on many different kinds of reservoirs. And that means that we design our devices, our sediment movers in-house. It's possible to scale them. We focus on the modular design. And the most important thing on that is we can focus on the specific reservoirs we have to work in. We can focus on the needs of the project. We can focus on the needs of the reservoir and also the needs of the authorities. So we can combine with our technology many different stakeholders and many different needs from them. At the end, I want to talk about what we already experienced. We had some projects in the past, and I want to tell you about one of my first projects I did. You can see it on the picture over here. It was a project in Italy, and there was a reservoir. It was in a recreational area close to Florence in Tuscany, and beside the beautiful nature we had there, we also had a lot of, I would say, natural forces working against us. For example, we experienced some flood events with very strong currents, where the lake usually was a still standing impounded water. It was almost a big river during a flood. So at the first flood, we were more or less surprised by it. So the sediment mover, the device was still inside the reservoir. And we could experience that it could consist this situation. Even with strong flows, it was still solid on the middle of the lake, and we had no big issues. The next time we pulled it to the to a safe harbor, as we call it, we at the beginning of the project we identify a place in the reservoir where the Sedimover can be pulled to automatically to be in a safe position, and by that being able to more or less decide on the program when to move over and when to stop the work due to flood events or other natural hazards. But we also experienced the opposite way, a dry fall. When the reservoir was totally emptied, our Sedimover was laying on the surface and waiting for the reservoir, for the water to come back. And also that was not a problem for the device. What was also the case, we did samplings beforehand for the project, and we designed our device according to the sediment samples we had. But when we've been on site, we noticed the sediment is even denser than we thought. So we added a jet system to the Sedimover, to the device, to be able to loosen the sediment even better than with just a mechanical cutter we had before. And in that combination, it was very, very easy to lose the sediment and then to transport them. Due to the floods we experienced here, we of course had a lot of debris entering the reservoir. And after having removed the first bigger parts, the Sedimover could just normally continue the work. So also debris was not a big issue. There were different other things, plant growth from the bottom in the summer, then power limits from the local net. And we also used a booster pump to prolong the transfer distance over here. And after that one, I went to another project. It was also in Italy, and there we faced totally different conditions. It was an artificial channel where they had their hydropower plant in, and the reservoir was at the end of an 11-kilometer long channel. So all the sediments which entered from the reservoir were first entering the channel, then flowing until the end, until it was stopped by the impoundment, by the dam, and then again transported to the river. Here we inserted the sediments inside the turbine water, while we had in the first project a bypass system to the downstream water. And because of this artificial manner the reservoir was constructed here, we had just fine sediments. There were almost no debris. The sediments were smaller than 1 millimeter in average, and we had steep concrete banks from the side. So besides the conditions of the sediment and the debris or the no debris, we had also to be aware to not harm the concrete slabs at the site. So we protected our cutter head at the bottom with another safety gear to prevent harm from the bags. And we also experienced a dry fall event over here. We could see that was a nice day. I was saying we could see how our Sedimover was working before. So how much sediment it already transported, and we could see the areas where we used the mechanical cutter, and we could see where we used the jet pump system. So it was really good that we could see something which is usually hidden below the water surface. That makes me come to an end. I want to summarize shortly what I just told you in that presentation, in that webinar. So I hope that globally we put the focus now more on the sedimentation of reservoirs and even more on how to find sustainable solutions to solve the sedimentation issue. And then I presented to you one sustainable solution, I think, might be one of the key technologies in the next upcoming decades, which is the sediment transport, to restore the sediment balance, the sediment continuity inside rivers. And I think it's a good approach because it can work fully automatic around the clock. It does not need operators. It's therefore a cheap system, and it's good to the environment because the sediment is still remaining in the aquatic system and not extracted then in other methods and other measures. So thank you very much. And I'm curious about the next speaker and the next presentation. Thank you.
Thank you, Lara, for this good presentation and this very nice equipment to help us to manage the sediment in the reservoir. Is an technology high-tech by this time, so it's something to be considered. However, maybe will be some questions from the participants. So when the time arrives, it will help us to respond the questions. Now I will call our colleague Elder Guta to present his thoughts about this subject. And after all, we'll comment and make observation and question for the two speakers. Mr. Elder, as I have already presented you and introduced you to everyone, so take the floor and tell us about the matter. Mr. Guta, the floor is yours.
Of developing countries like Mozambique that have some opportunities that may be greatly different from countries that have more existing and aging infrastructure. Europe, United States, Japan, etc., which have quite old dams. They really have to do a huge effort in maintaining or recover the storage capacity. Developing countries like Mozambique, we have more recent dams. In many cases, we will have less severe sedimentation problems. So adopting good management strategies may help to also avoid this aggravation of the sedimentation issues. But maybe most importantly is that we still have many very important projects that were not developed yet. We have several in mind, and the most urgent, maybe we could talk about Mpandankua, which is a national scale project as an example. And this type of issue should be thought about right from the design stage. Right from the beginning, adopt some design strategies that go in the sense of a better management of the sedimentation problems. Just as an example, now in the context of where I live, this is a dam that it's only 10 minutes from where I live, literally from my house here in France, just near Grenoble. And it's a runoff river dam, important to supply electricity to this urban area. And it's a small dam. It's only 16 meters high, but it's quite important in the production of electricity. And they have to draw down the reservoir, because staying several years without doing that to flush the sediments may lead to almost complete filling of the dam. This is the picture on the right of the last operation of flushing of the dam to release sediments. Now, the deposition patterns of the sediments depends on different factors. And one of the main factors is actually, okay, what type of sediments are in flowing to your reservoir. These are examples of videos that I will take during my PhD of experiments with different particle size. In this video, just notice it is exactly the same flow conditions, but with different particle size. We see that in one case, the first part, we have largest sediments. The sediments are transported near the bed, which what we call bed load. Whereas when we decrease for 3 times the diameter, we have a much more dispersed sediments with higher concentrations all over the depth. This is typically what we see in flood conditions with brown water transporting a lot of fine sediments. So actually how it will deposit depends a lot on this type of transport. Bed load or suspended load, large particles or small particles. Not only, but it's one of the main parameters. Here I show first the figures on the left. Large sediment, coarse sediment on the top will create a type of delta. They will deposit faster. As I shown in the video, they are transported more near the bed. And as soon as they enter the reservoir, they start depositing. And then the fines will deposit later, closer to the dam. And the figure on the left bottom, it's what we typically have if we don't have large sediments at all. We may tend to deposit straight near the dam, because it's only fine sediments. They will tend to more easily go a longer distance and then deposit near the dam. And then other factors also play a major role, like the configuration of the dam itself. Is it a narrow dam, a narrow reservoir, or a wide one? Is it a tall dam or not? This may also play a major role, but this coarse and fine sand is a quite well documented feature. So in numerical modeling of sediment transport processes can help us to predict such an evolution over large time scales. After 10, 20, 50 years, what may be the sedimentation pattern? And they are also very important because they allow to test which type of measures to manage sediments may be most adapted depending on the case. Talking about measurements, measures, I will just mention 3, which are among the most important, but not the only one. But these are 3 measures in different categories. We have mainly 3 categories of sediment management strategies. One will be reduce what comes to the sediment. So we avoid erosions in the catchment. We protect the surface. We avoid deforestation. So this can maintain a good stability of the soils and transport towards the dams. The other ones, which now deals with the way we operate dams, we have basically two similar measures, but are really different in what we try to assure. One is we try to pass sediments during flood seasons or during flood event, meaning that if we have the opportunity to keep lower levels during the floods and keep higher velocities going through the dam, we will allow the sediments to not deposit. Whereas the other one, it's drawdown flushing, in which we will lower the dam mostly in the dry season in order to erode the main flow path, which is basically the original channel. The figure on the right show from the temporal evolution after 2 days of flushing. After 8 days, we start seeing the channel from which the flows will occur, and it will erode and move the sediment that are in the channel. And then on the right, after 13 days, this channel starts becoming bigger, eroding the banks, etc. So these different measures have different limitations and advantages, and we have to, according to the case, evaluate which may be more adapted to our case. Again, these are not the only ones. We have many others, like bypass that Lara mentioned. It's one type of routing sediments to either with tunnels or other ways. And also removing sediments, it's a different category in which we may dredge or use other mechanical strategies to remove sediment from upstream to downstream. I just mentioned some of the measures that we may think about right from the beginning when we can, right from the design, or even in situations in which the sedimentation is not very aggravated. One example of these strategies right from the design stage, or to take into account the sedimentation problems right from design stage, in the case of Pat Bang Dam site in Mekong River in Asia, the figure on the right shows an idea of how concentration is distributed. The dam, it doesn't exist yet, but right from the design stage, try to understand how the transport occurs. Where do we transport more? Is it on the left side or the right side of the cross section? So where we have less sediments, that's where we want to have the turbines. Where we have more sediments, we want to place the gates that allow removing the dams, the sediments during flushing or sluicing. So right from the beginning, we see that for this case in particular, the sedimentation issue, it's taken really seriously. Now, I want to move to some reflections to the Mpanankua case, which I mentioned earlier, due to its importance for the country. It's a very big project. It's between Cahora Bassa Dam and Tete. It's quite an expensive project, actually. And we are developing some numerical models to explore some questions about this project. A first question and one numerical model that is being developed, it's a 2D model for dam break analysis, in which we want to understand the propagation time in case of a failure of the dam, given that we are near one of the major urban centers of the entire country. In case of failure, what are the propagation time to reach the city? What are the areas that will be inundated? In the video on the right, I show an example of the flow velocities since the failure of a dam up to Tete, and allows also to see the perimeter of inundated areas. It's a model that it's not yet completed, but it's already giving much information about these questions. So there we are exploring a 2D hydraulic modeling, which it's very adapted to this type of analysis. On the left, I show an example of a model that I've been working the last few years, which allows evaluating the flooding risk in the city Marseille, which is the second largest city here in France, and allows us to know the perimeter of the city that it's more exposed to severe flooding. But this is not the type of models to evaluate the topic that we are discussing here. The second category of models that we are developing regarding Mpanankua, it's now related with sedimentation issue. And what may be the issue here is that right upstream the Mpanankua, we have the Luya River entering or discharging to Zambezi. And the Luya River is one of the main affluents of Zambezi in Mozambique. It brings significant flow, especially during floods, but it brings also high sediment loads to Zambezi. So it brings a lot of sand to Zambezi. And this sand will mostly be trapped if no management strategies are adopted it will be trapped in Panankua Dam. And as Lara introduced before, two issues are to be managed here. One is the fact that without any measure, it will just continuously accumulate behind the dam. And this accumulation implies that we release clear water downstream, and the response of the river will be to erode until it reaches a new equilibrium that it's compatible with its new flow and sediment conditions. So the model being developed concerning this issue, it's only for the downstream part, actually, because I have not had access to data in the upstream part, data which is basically bathymetry, the topography of the river in this region. I do not have, but we had access to the bathymetric data from Panankua downstream. So a sediment transport model is being developed to simulate the transport processes with a reduction of input from upstream due to the dam. But a sediment transport model, it's quite complex, so the preliminary analysis should be developed on different issues, like what is the longitudinal profile of the river in the concerned zone. I show here in the figure about 0.2% gives an idea about the energy and the transport capacity in this region. And then in the figure on the bottom, it's actually the diameter of the sediments that are present in Zambezi in all this region. It's basically sand. So it confirms that indeed, and I will show another figure right after, this is the sand that actually will be reduced, and that Luya River contributes a lot in transporting towards Zambezi. It's in the range of 0.6 millimeters. And here, in terms of river morphology, I show the confluence between Luya and Zambezi. We see two things in the figure on the left. We see both bedrock, and if we look to the figure on the right, actually it corresponds to a gorge zone in which we have quite a lot of bedrock, but Panankua, it's located right at the end of the zone. After this gorge zone, we have a mobile sand zone. So that's the region that may be potentially heavily impacted by the reduction of upstream sediments. And in the picture below, I show a scheme of what could be a potential consequence of this reduction. But given that we have bedrock right at the dam site, this erosion will probably be a bit downstream, right when we enter to the mobile sand zone. And I show with the red line the correction of the original scheme, in which the bed may actually erode significantly when we enter the mobile sand zone. And as Lara also mentioned, one of the major impacts, for instance, is in terms of infrastructure. If we have severe erosion downstream the dams, again, I show a video of the experiments that I would carry during my PhD. And this is a very simple video that show how this scour around a cylinder, which represents a bridge pier, may occur. If we can just imagine the level of the entire bed in this section that it's being reduced, so the level of the scour will also be lower, and it may endanger stability of structures when we have them downstream. A last point in the preliminary analysis is actually the hydrology. I show here a duration curve that gives us an idea about the frequency of different flows, leaving Cahora Bassa Dam Mpanankua, it's not really a regulation infrastructure. Is to turbine the flows that already pass through Cahora Bassa. Its storage area, it's about 30 times smaller than Cahora Bassa, so it will not really regulate significantly the flows. So we will have roughly the same intensity of flows going downstream, but without the sediments. And this curve gives us just an idea about how frequent these flows are, at least leaving Cahora Bassa. And this is have been extracted from our host here, a publication from Matola, in which in the same publication we see that we may have several years without passing 4,000 cubic meters per second. But then during important floods, the discharges of Zambezi may also increase significantly. But this is a small portion of time. So we want to understand these frequent flows, but also the specific flood flows, which are shown in the table below, like 10, 20, 50 years floods, and to simulate how the river will respond to this type of intense floods in terms of erosion. This is one thing. And then the other thing is the long time evolution over, let's say, 50 years. We will run 50 years time series to see the response of the river and the adaptation downstream, and to have an idea about the erosion processes. Well, I show here an example of the type of results to be explored. On the left, the longitudinal profiles. This is for a small flood, like an annual flood, with 4,500 cubic meters per second, and then a cross section at a given zone to evaluate how this profile will drop and how the cross section will be modified. This is a very early stages of the refinement and calibration of the model. So please ask me in 5 months. The response right now, I don't have yet, because the model is still being refined and calibrated. To finish, monitoring is in my view one, if not the greatest challenge to properly apply the sedimentation management strategies, because often we lack of data. So are we able to say in our different dams in Mozambique, what are the rate of sedimentation in the different reservoirs? Without collecting data, it is difficult to answer this question. What data? Well, we need bathymetric surveys that may be really detailed, or just some cross sections. What sediments are present in the reservoir and even in the river? Can we measure the sediment transport itself? Often it will be sediment concentration. And also the other point is that it will be interesting also for the case of Mpanankua, if data is available, run these sedimentation models for the dam itself. This was not possible in the same way as the model downstream. As I mentioned, no data it's available of the bathymetry or even cross sections. If someone knows about the available data, I will be happy to take this data and start building the models for Mpanankua dam itself. And finally, it will be the interest of this type of analysis is to have in advance, as I mentioned earlier, an idea about the impact of this structure, which is such a large project and structure, it's important for us to anticipate the management of the structure or even the environmental impacts of this project. So I'm happy to answer some questions if you have some. Thank you.
Thank you very much, Mr. Elder. We appreciate a lot your presentation. You presented here science and practical issues, so we are very happy with that. Going ahead, I don't know if Mr. Baptista wants to say something before we go to question and answers. Mr. Baptista?
Thank you, Mr. Matola. I think we can proceed with the Q&A questions to our speakers. Thank you.
Thank you. I will make a short summary of those two presentations. The main issue that Lara presents is a new technology to make sediment balance in the reservoir, to make sure that the sediment don't just stop in the dam, but also pass through the dam to make this balance. We know that the water passes through a balance in the dam, but regarding sediment, we see that the dams trap the sediment, and so she's bringing here an idea of making this balance using a vessel that will be automatic to stack the sediment and take them to the other side. We will have some question about that. And Mr. Elder brought here something very important that we know, that to solve or to mitigate sedimentation, we have to go, first of all, to avoid the sedimentation using a very good soil management to reduce the sediment yield. Because when the sediment is there, it brings us a problem. You showed here how this sediment attract the large sediment and the fine sediment, the one that deposit at the beginning of at the entrance of the reservoir, and the fine one which goes until the dam and the sediment there. So also brought here the idea of dealing with this issue of sediment in the design of the projects. And we showed here the importance of that for this project that we have of Impanda Dam. So this is a summary of the presentation, and I invited anyone who wants to make a question that our speaker already prepared to answer. The floor is open.
Before Lara start, I think there is a question on the Q&A chat. I think the speakers can give an answer on that. If not, I can read.
Okay, read it.
Marius Raskau, you want to give, they want to know, to the sediment in the reasonable time frame, can the downstream sediment load be safely increased more than incoming sediment load?
I would take it as my question right now. I would say yes. It's of course depending on the flow of the downstream river, how much sediment can be transported, but usually the sediment concentrations can be higher than the inflow. So it is also possible to desediment the reservoir and not just only to equal the inflow and the outflow. In average, I would say with a basic version of the sedimover, we can remove up to 100,000 cubic meters of sediments in 1 year.
Okay. Another question?
There is a question from MJ Carillo. Can you have access to the chat?
But I just try to answer his questions as I would understand it.
Yeah.
So, as I understand the question, it's the difference between the hydrosuction effect, which is using the gravity for the desedimentation, and on the other hand, the system we use with pumps. And the main difference is the use of active pumps and active measurements. So I'm convinced that the sustainable as the continuous sediment transfer by using an active hydrosuction pump system is more efficient, better controlled, and more versatile. So instead of just using the hydrosuction effect, you use that plus the pump capacity. I hope that went in a good direction, your question.
Yes, and Lara here she's putting a question on the scale. Maybe to ask if this technology can be used for large dams and the large reservoir. I'm talking, for instance, for our lake, which is 207 kilometers long and 30 kilometers wide, with more than 60,000 million cubic meters. Is this technology good for large-scale dams?
Yes, I would say it is also useful for large-scale dams, as we can scale also the size. The sediment which is in my bag, for example, it's a small one. It's transportable on a truck, so it can be transported over the street. But that's I would say a small-scale sediment remover. If we scale it up, we use big hydrosuction dredges, big dredges, so then it is also suitable for large dams. And if one dredge is not enough, we can use 2 or 3 or 4. So we can also scale it in numbers. And because every reservoir is unique, of course, we need to talk about each one separately. But as we design our devices also at Hülskens, we can build it as it is needed.
Maybe you can talk about the cost of this kind of project, using your experience in the last projects. How the cost of ours?
We usually calculate prices per cubic meter. So with the sediment transfer, it is between, I would say, 10 to 30 euro per cubic meter, depending, of course, on the situation, on the sediment volume. The more volume you have, the cheaper is the per cubic meter price. And of course, the sediment density, the compactness of the sediment, if it's contaminated or not. So there are many factors, but in my experience, it was always between 10 to 30 euros per cubic meter. For
cubic meter of water or cubic meters of sediment?
Removed sediment. Cubic meter, removed sediment.
Okay. Thank you. Thank you. It's a figure to estimate something can be useful. I don't know if there's another question here.
Yes, there is 2 more questions from Marius. Marius, if you want to present your question, or you can read, it depends on you.
Hello, everybody. I'm talking from Canada, actually, interested in these technologies for North America too. So the question that I had was, what technologies do you use to locate the sediments in a reservoir and to identify where the highest priority area would be for starting the desedimentation?
Thank you for your question. We do bathymetries of the lakes, of the reservoirs, and we do at least one in front of the project in beforehand to estimate first how much sediment is deposited, and then we also do at least one after the sediment transfer, so when the project ends, to calculate how much sediment was efficiently removed. But we can also do it, of course, on a regular basis to see how much sediment was entering the reservoir at that site. And then, of course, we have the sediment measurements on the system. So during the project, we can also quantify the sediment we transported. So the sediment volume, which is now free in capacity. And with all this data, we can tell about the sedimentation situation, which is inside the reservoir.
Thank you.
There are two questions. First from Anna and another from Lara Gehrmann. Can you see Mr. Matola?
Yes, I can see. There's 112 there. Yeah.
Okay. I can answer. About the modeling tool being used. Okay. There is two questions from Lara. I will combine the answers. Actually, is in both cases the ECHADS models are being used both for the dam break analysis, 2D numerical modeling, and also the same software is being used for the sediment transport analysis. Both of them with ECHADS, 1D and 2D. I hope I answered. And then the maybe most sensible question about the data to being used to calibrate normally, or for new dams. Often we have little data to calibrate differently than like bathymetric surveys of existing dams, in which we can look over different periods and have a series of bathymetric data and calibrate our model based on this. If bathymetric data is not available over different dates to calibrate model, what we may be suitable to use is at least data on sediment transport. And in the case of Mpanankuwa, I've had access to recent bathymetric data, only downstream Mpanankuwa. That's why only this part is being modeled. But there is also some data on some sediment transport measurements, mostly of suspended sediment concentrations. But this will also be important to evaluate if the model is giving comparable results for given flow. Are we measuring or are we modeling comparable sediment concentrations and sediment loads to those that we measured before or not? So that's the data.
Yes.
There is a hand raised by Mr. Bonnet.
Yes. Can I allow Mr. Bonnet to talk?
Yes, good afternoon to everyone. Can you hear me?
Yes, perfectly.
Okay. First of all, I would like to thank all the two speakers and the moderator as well for sharing with us this important webinar on this sedimentation. Particular to Mozambique, and looking to the presentation that the speakers have made, and particularly Mr. Guta will talk about the future in Pandankua, and Lara as well on his experience on the management of the reservoir. I do think that both cases are related to the narrow gorges, which we are talking about the concrete dams, if I'm not wrong. But for Mozambique, particularly to the south region, where we have the open valley, we had our two biggest dams, which is Hurt Dam. One of it is Messenger Dam, which is more than 3 kilometers long. I don't know, I'm not looking for the answer, maybe we can think about that, and how all those modeling are applicable, or how we can convert them for the Hurt dams in such a case like this one. Thank you. Again, I'm saying that this is not directed even to Lara or Guta. If they can share, has some feeling or experience, yes, or someone who is following this webinar, it's just only to think and looking to the Mozambique as it is.
Maybe I can just share a few comments on my views. It is related with which sedimentation management strategies will be more adapted to that case, and how numerical modeling will be useful. One of usefulness of the numerical models, it's really this one, is the fact that we have different contexts that at least can be modeled properly. We may have to switch, for instance, from 1D modeling to 2D modeling, so that we capture better the transverse load that now in a wide reservoir may be more important than in a narrow reservoir, which is basically a more 1D configuration in the longitudinal direction. So for instance, just the fact that we move from a narrow to wide one, it may be determinant in choosing the type of modeling that we will apply. A 2D model will be more appropriate. This will be my first comment. And then this 2D model that simulates better these low velocities on the sides of the reservoir in the quiet zones will also allow to test if how this will be distributed all over the reservoir. And according to the type of sediments, is large sediments, fine sediments, also allows us to make the link between the type of velocities that we have distributed in the reservoir with the different management strategies that could be applied, because we can test it. Imagine that we operate the reservoir at this given level. What are the velocities? The sediments will then deposit or not, but it's for sure a more challenging scenario to model, but an interesting one also. That would be my comment.
Thank you, Mr. Guta. I think we are coming to the end of this webinar. Just thank everyone for participating in the discussion and sharing your questions. And again, any question raised, you can send an email to us or write in the chat. To end this webinar, I would like to invite Mr. Carlos Bonetti for close this session. Mr. Carlos Bonetti is the president of the Mozambican Commission on Dams. Mr. Bonetti, the floor is yours.
Sorry, Mr. Baptista, I want to say something before we close. To make sure that to all participants that in Cahora Bassa, there's a department leading of environment, and this department actually is doing monitoring of sediment which is coming in, and also in a period of 5 years we do bathymetry in the reservoir. But I cannot go deep on that to make sure that the sediment management in Cahora Bassa to make sure that everyone goes out and knows that there's something we are doing about sediment in Cahora Bassa. We can close, Mr. Bonnet. Thank you.
Thank you, Mr. Matola. And first of all, I would like to apologize by joining later during the connection problems here. In the last 24 hours, the 3,000 kilometers Mozambican coastal line and inland are being ravaged by a severe tropical storm called the Filippo. The consequences are not yet evaluated, but the turbidity in the rivers wherein, as well as the ocean, will have severe impact in the sediments. So this our section comes on time, and looking at the sediments in the reservoir, we also think about the increasing dam construction in the world, which interrupt the continuity of sediment transport to the rivers, resulting, of course, in the loss of the reservoir transport through the river, and also resulting in loss of reservoir storage and reduced use of land. These depriving downstream reaches of sediment essential to channel forming aquatic habitat. So, what we've done today, we're thinking about the improvement of the techniques of pass sediments through or around the well, the reservoir, to preserve the storage capacity and minimize downstream impact, which for Mozambican in particular, we have to also associate with the bad agriculture practice in rural and most areas, which becomes the situation more challenging. I'm sure that the time that we spent here is more 1 hour and a half. We have learned and achieved more effective solution with regard to the management of sediments in the reservoir. Particular to Mozambique, thinking about the future Mpandangua project led us to the serious consideration of this management of the sediment. And particularly, I would like to thank Mr. Guta in anticipating this sediment transport but modeling, which will be applicable in future to the reservoir sediments. I would like also, in particular, to thank Lara for the solution which she brought for the continuous sediment transport long-term reservoir. It was our first experience as MozCOLD, Moçambican Committee on the Lifestyle, to take along with this webinar. And I would like to thank everyone who attended this event, and in particular to the High Court Technical Committee on Sedimentation who supported this event as well. And thank you very much, and hope to see you very soon.
Thank you.
Do we have a to take a picture?
Sure.
Of participants?
Yes.
I just, the cameras are open for all.
Camera is on.
Yes. Thank you, everybody, for being here.
Thank you.
See you next time.